All right, Auto One, I hope you're well. We're going to be talking about engine classifications and different types of engines and just a little bit about their layouts at first, and then we'll look at rotary engine, diesel engine, two-stroke engine, etc. So first we're going to look at inline engines where all cylinders are in a straight line like this four-cylinder old school airplane engine. Um, these are found in 3, 4, and 5 and 6-cylinder engines, believe it or not, inline engines, but it's just where the cylinders are one right after another. Above 6-cylinder, they get pretty long, and the problematic with that is that if we have a longitudinal engine in a car, it makes the nose go out a long way before it can dive, so it tends to not be as aerodynamic. These days, you won't see hardly any longitudinal 6-cylinder inline engines except on BMWs till fairly new, actually. But everybody else has gone to the largest inline cylinders you'll see is a 5-cylinder pretty much. And that's Volvo and Mercedes, and typically they're transverse mounted. There are V-type engines like this one here, and they're found, like it says, on 6, 8, 10, and 12-cylinder engines. It's a more compact arrangement because you're putting more cylinders in a shorter distance. So there's 4 over here and 4 over here. Here's the center of the crankshaft, and it makes a V shape. There are 90-degree V8 engines. There are 60-degree V8 engines. So a little different designs depending on the manufacturer. But this is a little more compact. We can get more cylinders in a small area. And the more cylinders we have, like a V12 Jag, which is a pretty common engine, the more we get smoothness of operation. So next we're going to look at cylinder arrangements. We're continuing to talk about cylinder arrangements. Next one is a horizontally opposed engine. This is found, like it says, on 4, 6, 8, and 12-cylinder engines. They're very compact and smooth running. This is all the Volkswagens from 1939 up until the early or mid 80s. It's also Porsches from way, way back all the way up into the 90s. This one has 2 cylinders going out here, 2 cylinders going here. So it's very compact in terms of height. It's a fairly wide engine, but fairly compact. One of the really modern cars, or the only cars using it besides Porsche now, is Subaru. And Subaru use it in both 4 and 6-cylinder configurations, but mostly everything is 4-cylinder. So all those Subaru Outbacks, almost all of them are horizontally opposed 4-cylinder engines. We also call this a flat engine, okay, or a pancake engine. So that's a horizontally opposed engine. So all the Volkswagens, Bugs, Vans, Squarebacks, Fastbacks, Karmann Ghias, and the Thing, that is a car, all had horizontally opposed or pancake flat 4-cylinder engines. The Corvairs of the 60s had a horizontally opposed 6-cylinder engine that was air-cooled. And most all of them were air-cooled, by the way. The next one we want to talk about is another category, which is valve arrangement. So instead of just cylinder position, now we're looking at valve arrangement. And the L-head engine, which is really called a flathead, or what people call a flathead engine, the L-head was where we had a piston in the block and we had our valves in the block. So the valves were in the block. It was a very, very simple design. This is basically all the Ford Model A engines, etc. That's it. Low compression engine, really easy to do. I'll bring the camera over here and we'll look at a flathead engine on a that we have for a lawnmower. So the piston's here in the block and the 2 valves are coming up and they're in the block, and the cylinder head, all it does is it has the combustion chamber and it has a spot for the spark plug to go back in. So we'll come on back over here and hopefully I didn't make you too seasick. Okay, so let's continue on here. So our next valve arrangement category is what we call an I-head engine, or what most people call the overhead valve engine, or OHV. Here's a little animation of it going. There's the crankshaft spinning. It's an inline 4-cylinder engine in this case. This is a non-overhead cam engine. It's a pushrod engine or an overhead valve engine where you have the camshaft down in the block. You have these hydraulic valve lifters. You have these pushrods. You have these rockers, and these were all 2 valve per cylinder engines, 1 intake and 1 exhaust valve. And you can see how the cam eccentric pushes up on the lifter, which pushes up on the pushrod, which actuates the rocker and pushes the valve down. So, like it says, valves are over the cylinder in the cylinder head, and this uses a rocker arm and a push rod. Sorry, um, just like that. So, get a good look at that. This one happens to use a timing chain, and very, very simple design. So this is pretty much everything that I learned in high school was overhead valve, or what we call push rod engines. Very, very few of these made anymore. The only place I've seen them is in some trucks, and General Motors, the only one. And I don't know about in 2020, but fairly recently they still were making a overhead valve push rod engine. Next valve arrangement we have is overhead camshaft, or OHC. This is where the cam, or short for camshaft, and the valves are in the cylinder head. So the one that I have down here on the table is that type. This cylinder head right here is an overhead camshaft engine. This one is, like all modern engines, is 4 valves per cylinder, 2 intake, 2 exhaust. You can always identify the intakes because they have a larger head diameter and the exhaust have the smaller head diameter. This one this is actually a dual overhead camshaft. The camshaft goes here, the camshaft goes here. Here's one of the camshafts for this engine that bolts into there to open up valves. A lot more valves in this engine. This is a V6, so it's what we call a 6 times 4. It's a 24 valve engine. It's a pretty simple design to have overhead cam, because here's the camshaft up above. In this case, pushing on what's called a cam bucket or follower and pushing right down on the valve. We do in this case have a timing belt or chain running the 2 of them. These work really well at higher RPMs, so they're fast accelerating. They're good for small engines. So we can have a single overhead cam, which is one camshaft, or we can have separate cams for intake and exhaust, like the one I just showed you right here, which is a dual overhead cam. This V8 here is a dual overhead cam. You can see 2 cam gears here, 2 cam gears here. The crankshaft is driving a chain which drives these 2 gears, and then there's a separate chain that drives these 2 gears. So there's a camshaft here for exhaust, a camshaft here for intake, camshaft here for intake, and a camshaft here for exhaust. So I'll take the camera and walk over here, and hopefully, again, not make you seasick. And we will see if we can look at a couple of engines over here. So this one here, that I've got the plastic on, I'm pulling off right now. You can see right here a cylinder head with 2 gears, and you can see the chain running off the crankshaft. I have the other cylinder head off. That's the one that's over there on the bench that I was just showing you. This V6 Ford engine is the same as that one. That one's fully assembled. This one's about halfway taken apart. Okay, so we'll come back over here and we will continue. And we'll look up here. So there's our animation still going for overhead camshaft engine. Another way of classifying engines is by cooling system, and air-cooled engines, which were where we blew air over these fins, these sort of horizontally running metal pieces we call fins, these running vertical here, these running vertical here. So this would be an air-cooled engine. This was Volkswagen, Porsche, Corvair. They were all, and many motorcycles for that matter, they were almost all air-cooled up until the federal government outlawed them in starting, I think, I think it was in the early 90s. I'm not 100% sure. Might have been actually the 80s, because engines that are air-cooled typically pollute the environment more, so we no longer allow them on any road in America. Now, there may be still some dual sport motorcycles that are air-cooled that I don't know about. Dual sport, and you can ride them on the dirt and on the street. I'm not 100% sure about that. If we walk over here, we'll look at this Briggs & Stratton lawnmower engine. You can see the fins here for cooling. You can see the fins on this 2-stroke engine, on this 4-stroke engine, on this 2-stroke engine. You can see the fins on there for cooling, so we can identify those as air-cooled engines. And get you back over here. Okay. Let's keep going. So next cooling system is our liquid cooled system. And let me just move this back over just a hair. And so most all cars are liquid cooled, and this is where we have liquid cooling, the extracting the heat of combustion, which runs about 2,500 degrees Fahrenheit. We've got to get rid of a lot of that heat. Most of it goes out the exhaust. Okay. We say water, but it's really 50. We use 50% water and 50% antifreeze to prevent corrosion, prevent freezing, and other things like that. So water and antifreeze are circulated through water jackets to the radiator for cooling. So here's an automotive radiator. Air is going to be passing through the radiator, extracting heat out of that liquid. A water pump's going to be pumping that coolant back in through the block, up through the cylinder head, through the heater if the heater is on, out through a thermostat when the car gets hot enough, and then back to the radiator for cooling. So it's just circular liquid cooling system to help extract some of that heat of the exploding gasoline and air, again, which is about 2,500 degrees Fahrenheit. Um, Another way we can talk, so that's our third category, which is type of cooling system. Another way we can talk about engines is their displacement. That is the combined cylinder volume of all the cylinders. And we come up with that with the volume of a cylinder is pi r squared times the height of the cylinder, which we call the stroke. That's how far the piston is moved by the crankshaft from top to bottom, top dead center TDC to bottom dead center BDC, times the number of cylinders. So if we have a V8, we find out the radius of the cylinder bore. So we go pi times the radius squared times the stroke, and we come up, multiply by the number of cylinders, and we get the cubic inch displacement of the engine. So we used to do everything in cubic inches or CID. Now we do most everything either in cc's, or we really do everything in liters. There's 1,000 cc's per 61 cubic inches per 1,000 cc's, or 61 cubic inches per liter. So now the Chevy 350, which was 350 cubic inches, we call a 5.7 liter engine. Okay. So that gives us a way of talking about engines. We can say I have a large displacement engine, I have a small. You can say, oh, I have a 350, or I have a 400, or I have a 1.8. We're talking about the volume of the combined volume of all of the cylinders. Again, volume of the cylinder, pi r squared, times the height, and then times the number of cylinders. Next, we can classify engines in terms of horsepower. And some of the pictures like this one's kind of fun. But horsepower is a measurement of an engine's ability to perform work. And it's measured in foot-pounds of work per minute. 33,000 foot-pounds per minute is 1 horsepower. And they developed this way of measuring power in the mines. It was how much weight a horse could pull in a minute, okay? Pulling coal or whatever they were pulling out of a mine. So we say that horsepower is the top speed or high speed power. It's the speed you feel when you're going 70 miles an hour and you just romp on the throttle. You're typically feeling horsepower. So there's a Hemi Cuda doing a burnout. And I guess that's what they do in other countries. When the car wears out, they add a horse to it. Just kidding. Torque is another measurement of power, and we can talk about engines in terms of torque. Torque is a twisting force. It's the low speed power of the engine. So this giant mining truck here, where you can see the guys only to the middle of the tire, is probably a 6-foot person. This is probably a 12-foot tall tire. That truck doesn't need to go very fast, probably goes no more than 30 miles an hour, but it needs to carry a tremendous amount of weight. So we need low speed or twisting force torque. It's the power you feel when you accelerate from a stop sign, the pull of the vehicle. That's the torque of the engine. The RPM, just a related term, which is revolutions per minute, that's the speed at which the crankshaft is spinning. So we typically idle like 500 to 900 RPM at 60 miles an hour. Many cars are going like 2,000, somewhere between 2,000 and 2,800 RPM. And our max RPM on most cars is 5 to 7,000 RPM, or what we call red line. Here's a tachometer, which measures the RPM of the engine. So this is times 1,000, so that's 1,000, 2,000, 3,000, etc. And up here in red is 7,000. So it's what we would call the red line of the engine. We don't want to take the engine any faster than that, because when you do, if you take an engine too fast, what typically happens is the rod bolt fatigue stretches, breaks, and this comes flying off the crankshaft and does all kinds of damage to the engine. That was a Toyota Camry that died up on the grade. Let's keep going here. So now we're going to switch gears to, automotive pun intended, by the way, to a Wankel engine, which is also known as the rotary. I don't think Mr. Wankel's name was very popular, just supposing. The rotary engine, rather than a reciprocating engine, so instead of having pistons that go up and down like this, the rotary engine has a rotor, like you see here, sort of a triangular shaped rotor, and a rotor housing, which they call an epigicoid curve. It's kind of like a kidney bean, kind of comes in there, etc. They call that the rotor housing. It doesn't have a crankshaft, but it has what we call an eccentric shaft in the center, which you can see right here in this picture. It has ports, which are just holes in the rotor housing instead of valves to let air and fuel in and to let exhaust out. They're really powerful for their size. They're quite small. I'm going to show you one in just a second. They're fairly smooth running, but they get poor fuel mileage and they're really difficult to meet emission standards. So they're polluting engines and they don't get good gas mileage. Again, powerful for their size, smooth running, but the two strikes against them are poor fuel mileage and significant pollution. I'm going to go ahead and take this again, see if I can get you seasick, and walk over here and look at a rotary engine that we have over here. So this is a rotary engine. This is the rotor housing here. There's the triangular shaped rotor, and there's the eccentric shaft. And you can see this guy spins like this. Each one of these rotors faces is the equivalent of a cylinder. So one rotor is the equivalent of 3 cylinders. And this engine actually had 2 rotors and 2 rotor housings. So those 2 rotors were the equivalent of a 6-cylinder engine. And I think you could notice that it really was quite a small engine, and very compact. But again, not good gas mileage, and they do make significant pollution. So here's a rotary engine just showing it spin. There's holes in the rotor housing we call ports. And so when this guy moved like this, it made a low pressure and sucked in air and fuel. Right now, we're pushing out exhaust here, and right here, this one's on compression. And well, it's end of compression, beginning of power. The spark plug is going to ignite that. The explosion is going to spin this like this. So it's spinning in kind of an eccentric direction. So this is just showing air and fuel coming in on intake where it's starting to compress. You get a spark and you get explosion, and then power, and then you're going on exhaust. So air and fuel coming in that port and then going out there. There's a 2-rotor rotary engine with a manual transmission behind it. Okay, so let's talk for just a moment about two-strokes. Two-stroke motorcycles and small engines. Unlike the 4-stroke engine, which does the intake, compression, power, exhaust, 4 strokes in 2 complete revolutions of the crankshaft, this is going to do intake, compression, power, exhaust in 1 revolution of the crankshaft. So we just say it's got 2 strokes of the crankshaft, down and up, and that's it. Very, very small engines. They have some advantages and some disadvantages. We use them in motorcycles, chainsaws, outboard motors, etc. It is illegal in California to, you can't sell, and I think it might be America, but I know California for sure, you can't sell a brand new 2-stroke anymore. They're illegal because they're pretty polluting. There are some freshwater lakes where they don't even allow you to run them, but most lakes and the ocean, you can still run a 2-stroke outboard. You just can't buy a new one. So I have a Suzuki DT40. It's a 40-horse 2-stroke, and it makes 1 power pulse every revolution of the crankshaft. So they're very powerful. Their gas mileage isn't that great. The pollution is not very good, but they make a lot of power. So you get 1 power stroke per revolution, REV for revolution of the crankshaft. They use ports instead of camshaft and valves, so kind of like the rotary engine. They don't have valves or a camshaft. They just have holes that get uncovered by the piston. So like you can see on this piston right here, it's at the top. Here's a hole. So this is called a transfer port. Air and fuel are going to come down into the crankcase. When the piston goes down, sorry, that's the intake or the inlet port, not the transfer port. Transfer port's over here. So as the piston goes down, it's going to push air and fuel out through the transfer port, and then it starts to go up into the cylinder. It fills the cylinder as it comes up. So we'll look at this a little further, but basically when the piston's up at the top, air and fuel's going into the crankcase, you get a spark plug and an explosion. That's forcing the piston down. Simultaneously as it goes down, fresh air and fuel's going back up, and the black is supposed to be exhaust. Exhaust is being pushed out. So the reason why it's so polluting is you'll get fresh unburned air and fuel going out with the exhaust, and that's polluting the environment with hydrocarbons and carbon monoxide. So there's very few moving parts. You got a air cooled, you can see the fins block with a little cylinder head with a spark plug, or piston rings and connecting rod, and a small crankshaft. I'll show you a couple of these in just a moment. Oil must be mixed with gasoline on gasoline two-strokes. Not true of some diesels. There are diesel two-strokes where we don't mix oil with the gasoline. They've got a lot of power for their size, but like it says down here, they have poor fuel economy and they pollute a lot. One of the beauties of a chainsaw and a weed whacker is you can actually invert them. You can go up over your head and they'll still run. You can't do that with a car. I know they do it in Hollywood, but you can't do it with a car because when you go upside down, now the oil goes out of the pan, the oil pump would suck air and the engine would starve for oil and eventually seize. So this guy going up a really steep hill, he's still going to run fine. These will run fine, etc. Let's walk over here and look at a couple of two-stroke engines. So here's a two-stroke here. That's a two-stroke back there. And I'll pull this one out and get to where we can kind of talk about it. So the way this guy works, move this partial Chevy 350 head. So the way this guy works is you've got a very small crankshaft and a piston. The rings are taken off it just so I can spin it easily. But what happens is when this goes down, here's the inlet port here. And when it goes down, the piston's creating kind of a negative pressure. It's pushing down, and air and fuel will go up through here in this transfer port and come into the cylinder here. It's got this really interesting looking shape on the top of the piston, which helps the air and fuel to come in and fill the cylinder. And then we're going to compress it, and then we get a spark, and then it gets an explosion. And when we go back down, we uncover the exhaust port back there. Fresh air and fuel is being forced in by the negative pressure, I should say the descending motion of the piston pressurizing the crankcase pushes fresh air and fuel in, but simultaneously pushing the exhaust out. This is a little muffler. So again, we'll start at the top, we'll go down, we're getting intake and exhaust at the same time. We compress it, we get a spark, we push it down on power stroke, we intake and exhaust at the same time. We go up on compression, we get a spark. So really cool engines, really small, compact, powerful, light, make a lot of power for their size and weight, and really, really neat engines. But they're just kind of polluting, so it doesn't work so well. Here we go. And then right down here, more difficult to cool than a four-stroke, and that's because you're making twice as many power strokes. You're getting a power stroke for every revolution of the crankshaft instead of 2 revolutions of the crankshaft like you did in a four-stroke engine. Let's look at diesels now. So diesels are heavy engines that are found in trucks and more passenger cars these days. 5 years ago, we thought that diesel in passenger cars was going to be the wave of the future, but more and more we're having trouble meeting emission standards with oxides of nitrogen. We started to steer passenger cars, a few of them, towards diesel, and now they're kind of coming back towards gas. As in terms of new technology, really looking at now, diesel's not going to be clean enough for us, though they use it quite a bit in Europe. It's just a lot more polluting for our standards. So in diesels, we're going to burn diesel instead of gasoline. Now they're both made from crude oil. Diesel's a little less refined. Diesel has more energy per gallon. A gallon of gasoline at sea level has about 114,000 British thermal units. A British thermal unit is the heat energy that it takes to raise the temperature of 1 pound of water 1 degree Fahrenheit. So gasoline has 114,000 BTUs of heat energy per gallon. Diesel has about 140,000. So about 20% more energy in a gallon of diesel. There's no ignition system. They're what we call compression ignition engines. I think that's going to say yeah right there. Compression ignition engines. That is the heat of compression. When we squeeze air and fuel into a really tight volume, diesels will run like 20 to 1, 22 to 1. The friction between the molecules of air and fuel, because they're pushed into such a small volume, their heat goes up dramatically, and then we inject diesel and it spontaneously combusts. We don't use any kind of ignition system or spark system. They have really good fuel economy and really good power. Their power to weight ratio is amazing, but and turbocharging helps raise their power level. So here's a turbocharger here. This engine has 2 turbochargers. There's a turbocharger there. All a turbocharger is an exhaust-driven air pump. Exhaust going out of the engine starts spinning a fan, which spins a common shaft, which spins another fan, which pushes air into the engine. If we can pressurize the air, we can get more than 100% of air into the cylinder because it's pressurized. So maybe we can get 105% or 110%. All of that oxygen combined with the fuel gives us tremendous power. So we turbocharge most all diesels, and we also use a blower as well. A blower is a gear or air or a belt-driven, gear-driven pump is called a blower. A belt-driven air pump is called a supercharger. A turbocharger is an exhaust-driven air pump. I'm going to show you all of these right now, or at least to show you the supercharger and the turbocharger. So here's a Mercedes turbocharger that was replaced on warranty, and here's a cutaway of a turbocharger. The exhaust is spinning this fan here, and this fan is pushing air into the engine. There's another turbocharger there. Here's a supercharger, which is a belt-driven compressor. That's how it sits on the engine like that normally. That's a pretty small supercharger. Superchargers make more power than turbochargers, but they also cost us power. They cost us horsepower to spin them. Whereas a turbocharger, in essence, is kind of free energy or free power because we're using the exhaust going out of the engine to spin this. So, all right, let's keep going. That's it. Okay.